now we will consider charged conductors and see what we can tell about the potential on the surface, inside the conductor, and also outside the conductor. So consider this charged conductor. Okay, it's an arbitrary, it's of an arbitrary shape. Now, and we consider 2 points on the surface, A and B. Okay, so we have a charge. This charge is distributed over that conductor. The electric field is normal to the surface of the conductor, as we have learned. It is not necessarily uniform when the conductor is irregular, as we have also seen. And we consider 2 points, A and B. Now, E dot ds, as you go over any path while you are at the surface, while you remain at the surface, if you go through any path on the surface, then definitely E dot ds is equal to 0. Why is that? Because any path on the surface means that it's a path where E is perpendicular to that path, because E is perpendicular to any ds, infinitesimal displacement on the surface. So this is the case for any path. And therefore, when you go from A to B, okay, then E dot ds is always equal to 0, because A is always perpendicular to any ds that lies between A to B. Now, the meaning of this is that the potential difference between A and B is equal to 0, because simply VB minus VA would be integral from A to B E dot ds. But if this is 0 all the time, then VB minus VE is equal to 0, and the meaning of this is VB is equal to VA. Okay? So this is the main result. A and B are 2 arbitrary points, and so the potential difference between these 2 arbitrary points in the surface, at the surface, is equal to 0. So what does this mean? It means that for all delta V equals 0 between any 2 points on the surface. This means that the surface of a conductor in electrostatic equilibrium is at the same time an equipotential surface. All the points on that surface are exactly at the same potential, There is no potential difference between them. This is a very important property of conductor. Of course, this is true when you have conductor in electrostatic equilibrium. Now, there is another important consequence of this, is that it's not only the points on the surface that are at the same potential, but actually the points within the whole conductor are at the same potential, and this is equal to the potential at the surface. And to see this is very, very easy now, I think. It is from here. Consider this is your conductor. Take any arbitrary point here, A, and take another point, B, which is just below the surface. Okay? And if you want to take any arbitrary path from A to B, then VB minus VA, what is this? This is the integral from A to B E dot ds. But in order to carry out that integral, you have to carry it throughout the material of the conductor. But E here is 0. And therefore, this is 0. So the potential difference between any point inside the conductor and a point on the surface is equal to 0. And since A is arbitrary, then this means that any point inside the conductor will be at the same potential as at the surface. So the conclusion is that even for a charged conductor, even if the conductor, of course, is not charged also, the same applies, the potential for any point inside the conductor is constant. All the points inside the conductor are the same potential, and this potential is the same as the potential at the surface of the conductor. Okay? This is a very important property of conductors. So any conductor which is in static equilibrium have all the points in that conductor, whether inside it or at the surface, at the same potential. Now, let's consider another situation which is a bit different, where you have here a cavity inside the conductor. So this is the material of the conductor, and here it's vacuum or air. Okay, so we will show now that the electric field inside this cavity is equal to 0. Okay, now we have mentioned this when we discussed the property, the electric field of conductors, and we said that we will prove this when we consider potential. Okay, so the question here, we know, for example, that we have seen before that if you have a conductor and the conductor is not hollow, the electric field inside the material of the conductor was 0. We have seen that this goes with electrostatic equilibrium. This is the meaning of electrostatic equilibrium. But when this conductor has a cavity inside it, okay, then the argument of electrostatic equilibrium alone we cannot be used to justify why you have 0 electric field inside the conductor, inside the cavity here, because here you don't have material of the conductor. Okay, it's just space or free space or air or whatever is this. Okay, but the fact that the whole conductor is at the same potential actually will serve to prove that the potential the electric field inside the material inside the cavity is equal to 0. For this purpose, I choose 2 points, A and B, which are just at the inside the material of the conductor, but just at the inner surface of the cavity. Okay, and I connect them by an arbitrary part. Imagine there is an arbitrary part between them, and of course I'm assuming here that there is no charge inside the cavity of the conductor. When you have a charge inside the cavity, as we have seen, things change. But I'm assuming here that I have a cavity with no charge inside it. So the result that I will derive apply only to that particular, with this particular situation. Consider this integral. Find VA minus VB, and which is equal to this integral. But I know what is the answer. VB minus VA is equal to 0, because A and B are within the material of the conductor, but just at the surface of the cavity. Why? Because the whole conductor here, the material of the conductor here, the whole conductor is at the same potential. So VA equals VB, and this is equal to 0. So this integral should be equal to 0. Now, since this path is arbitrary, and this is true, and this integral is 0 for all paths, the only way that this is possible is when you have the electric field inside the cavity equal to 0. So this is how we derive. Okay, because the result is path independent, then the electric field must be in 0. Okay, because this holds for any path, so it's not specific for a given path, because you know the potential difference, and when you find the potential difference, this expression is path independent. Okay, this result is path independent, and so this must be a property of the field, not the path, and therefore the field inside the conductor, the cavity here, should be 0. So this is a proof of a statement that we have made earlier, that even if you have a cavity inside the conductor, then the electric field is 0, not only within the material of the conductor, but also within the cavity. And a consequence of this is that points inside the cavity are all at the same potential, and they are at the same potential as points within the material of the conductor. Within the material of the conductor. To see this, take A, for example, to be within the cavity. Okay, so E now is not in touch with the conductor. It's a point inside the cavity, in the space inside the cavity. And consider this integral. Keep B here, if you like, at the surface. Consider this integral. Okay. Now, I know, but now when I'm considering this integral, I know now that the electric field along this path is equal to 0. I know now that I have just proven that the electric field inside the path equal to 0. Therefore, this now is equal to 0. Okay? And therefore, V beam and minus VA is equal to 0, and B and A are at the same potential. So this means that, and since A is arbitrary, and B is also arbitrary, then this means that there is no potential difference between any point within the cavity and a point within the material of the conductor. You can even take B here, not necessarily on the surface, take it whatever you like, okay? The result will not change. The potential difference between any P, any A inside the cavity and any P, any A on, within the material of the conductor is 0. So all points in the cavity are at the same potential as all points within the material of the conductor. And the meaning of this, of course, is that the points within the cavity are at the same potential as points within the conductor. So the whole conductor now, including the cavity inside it, given that it doesn't have charges, okay, is at the same constant potential. So this is the conclusion. Now, let's consider a specific conductor and try to calculate its potential. Our specific conductor is a charged sphere, and it carries some charge, and this charge is distributed, and it will be distributed uniformly on its surface, as you can expect, and it will be at the outer surface. I want to find what will be the charge or the potential of this charge. Now what I know, because this is a general conductor, is that the potential at the surface and within the material of the charge is the same. So what is this potential? Let me start by the following observation. Let me recall the shell theorem. What was the shell theorem? The shell theorem says that for any spherically symmetrical charge distribution, the electric field outside that charge distribution is the same as that of a point charge with the whole charge of the spherical charge distribution centered at the origin. Okay, so if you replace this charge distribution with a point charge with the same magnitude and centered at the origin, then the electric field outside that spherical charge distribution will be the same as the electric field generated by this point charge. And we have seen manifestations of this result in many situations. So since outside here the electric field will be that of a point charge, then the potential outside will be that of a point charge, because what gives rise to the potential is the presence of electric field. And therefore I know what that electric field for points outside the charge is just kq over r, where q is the total charge on the sphere. Okay. Now when I approach the surface, therefore just at the surface, therefore the electric field, the electric potential will be this. Just let R capital B capital R, and this is the potential at the surface. But having found the potential at the surface, I can find the potential for the whole sphere, because the whole sphere is at the same sphere is at the same potential as the surface, and therefore this is the potential of the whole sphere, okay? So inside the sphere and the surface of the sphere, they are all at the same constant potential, which is this, because you know, for fixed R, the R is fixed now, okay? So it is a constant potential. So this is the constant potential of the sphere. Outside the sphere, the potential is a function of R and drops as 1 over R, as you can see. So this is the potential. This is shown here. This is the potential. Between 0 and R, it is constant, as you can see, as kq over R. Outside the sphere, it drops as 1 over R. Now let's remind ourselves what was the field. The field inside the conductor was 0, because this is a material of a conductor. So the field between 0 and R is 0, and then after that it goes as kq over R square and drops, which is just the electric field of a point charge. So this is the charge of, or the potential of a charged conducting sphere. This, of course, result is independent of whether the charge on the sphere is positive or negative. This applies for both positive and negative charges, evidently. Now we consider an example where we have two conducting spheres, one of radius r1 and the other of radius r2. r2 is smaller than r1. These spheres are separated by a distance which is larger than their dimensions, so that the charge on one of them, the charges on them on one of them does not affect the charges on the other. This is the assumption. The distance is large enough so that the charge here does not alter the charge distribution on the other sphere. Okay, and they are connected by a conducting wire. Now, the meaning of that they are connected by a conducting wire is that they are a single conductor. And when we say a single conductor, this means that the whole conductor will be at the same potential. So this sphere and this sphere, when they reach static equilibrium, the thing that you can say is that they are both at the same potential, because when they are connected, of course, because they are now a single conductor. Okay, so the general rule: if you have two conductors, bring them in touch, the charge will redistribute itself so that they are all at the same potential, because they become a single conductor now. Okay, so this is what we know about them. Now, at equilibrium, the charge on R1 on the sphere with R1 is Q1. The charge on the sphere with radius R2 is Q2. This is after they come equilibrium and they have the same potential. Now, and of course, they are uniformly distributed on their surfaces because they are far apart from each other, and they do not alter the charge distributions. We want to find the ratios of the magnitude of the electric field at the surfaces of the sphere. That's find the ratio between A1, the electric field just at the surface of the sphere with R1, to that of E2, which is the magnitude of the electric field just at the surface of the sphere which has radius R2. This is the ratio that we want to find. Okay? Now, this is the potential of each of these spheres. It is the same. Okay? So this is the potential of a charged sphere. So this is the potential of sphere 1, and this is the potential of sphere 2. Now, the electric field, use Shell's theorem. The electric field just outside the surface is that of a point charge. Okay? So for sphere 1, it is kq over r1 square. For sphere 2 is this. And this is the ratio. Now, express this electric field in terms of the potential. So it is just V over R1. This is V over R2. And if you do this, they cancel, and you get E1 over E2 equals R2 over R1. Now, E1 is the electric field at the surface of the large sphere, and that is the electric field at the largest of the small sphere. Now, note that the ratio of the electric fields is inversely proportional to the radiuses, the radii. In other words, E1 in this example will have the ratio of E1 to E2 will be R2 to R1. This means that E1 is smaller than E2. The meaning of this is that the sphere with larger radius will have an electric field which is at the surface smaller than the sphere which is at the same potential but has a smaller radius of curvature. Now, this result explains why we have stronger electric fields near the sharp edges of conductors. You can think of the conductor as being built up actually of many spheres that are brought together, welded together, and so that at sharp edges the spheres there are of smaller radius of curvature, so the electric field there will be larger. Okay, so this is how we can utilize this result to understand the fact that the electric field near sharper edges on a conductor is stronger than it is near the flat edges. Now, this is an application or an extension of the just last example, and try to work it out yourselves.